Welcome to 1.2, page 4. We're talking about functions and cubic cookie elf factories and domains and good stuff like that. And page 4, first couple problems, pretty easy, but I think it's very, very important. In this day and age, it's probably more important that we can have our calculator answer questions for than it is that we can go through the process as we move forward. So they actually want us to use a graphing calculator to graph the function and then use that to find the domain and range. So we'll talk about domain and range, but let's go ahead and let's get this graphed. So we go into y equals. I'm going to clear out this old one. I want square root, which is second x squared over here. I want x. Now you could do caret for a raised power and then put 2, but if it's squared, squared's used so regularly, there's a special key for it. X squared plus 1, always double checking. And a good place to start for these would just be zoom standard. Some times you just hit graph and take a shot at it, but if I go to zoom standard, what it does, zoom standard is zoom 6, standard 6. Good one to remember. I don't have all these memorized, but I definitely have zoom standard. So if I didn't do that, if I went back here, I could just go zoom 6. I'm going to hit 6 right now on 3. 1, 2, 3. Now what zoom standard does is it sets up the minimum of -10, the maximum 10, the minimum on the y-axis -10, the maximum on the y-axis 10. If I went into window to look at that, we'd see it. It does all of this stuff for us. It has our x scale 1, which means every one unit, every integer gets a tick mark. Okay. Delta x, this is all about like when we're tracing and stuff like that, but these things we'll work with quite a bit. And sometimes it can be tricky, but anyway, here's our graph. Okay, so I've got this graph, and for domain I want to look left to right. Now, am I led to believe that this graph might stop somewhere? It actually could if I just looked at this. Maybe that's the actual end of the graph. However, I look at the function and I'm like, you know what? I can put bigger and bigger values of x in there, and I can put bigger and bigger negative values of x in there. Therefore, this graph, I would not have to lift my pen from left to right. It exists forever. So the domain is, remember this from the last page? All real numbers. Now for range, for domain, we scan from left to right. So it's -infinity, it exists to infinity. So we could say this is -infinity to approaching infinity. That's equivalent to this. We probably would go with all reals. For range, we scan bottom to top, and this graph does not exist until we get up. It appears to be right here at 0, 1. It appears like the first y value on there is 1. And we could make a good argument by looking at this and saying, sure, if I put in 0, I get square root of 1. Square root of 1 is 1. If we're not certain, one thing we could do is we could go second calc minimum. I want to know where that thing bottoms out. I want to know where that minimum of that graph is located at. So I'm going to go minimum, enter. It says get to the left of it, enter. Get to the right of it, enter. Do you want me to guess? Hit enter again. That's just, I've always thought that was weird that they say guess. And it says the minimum occurs when x is virtually 0, and it probably is 0. We always get this little rounding error when x is 0. But y is 1. 1's the minimum. So our range is f of x is greater than or equal to 1, which interval notation would be include 1 up to infinity. Bottom to top, doesn't exist until 1. It now exists and continues to exist forevermore as we increase. Okay. Y equals number 70, absolute value. Now you could always go to catalog, and it's not inconvenient at all because absolute value is right near the top of the alphabet. You can go second catalog, and that has like all these different things you can look at, and it just so happens absolute value is the very first one alphabetically. you also, I believe, abs window. Oh, look at that. Abs or alpha window. Let me do that again. Alpha window gets a lot of these things from the catalog that they think, hey, these are ones that you may use more than others. And really, this serves us extremely well. For this course, we're going to use all of those except, well, we're going to certainly use 1, 2, 5, 6, 7, 8, 9, and maybe 3 and 4 a little bit as we move into deep into second semester. So anyway, I'm going to go back into y equals. Quit. Y equals, I'm going to go alpha window absolute, and you can get it from catalog, and I'm going to put in 3x minus 5. And I'm in zoom standard now, so you could just graph or just hit zoom 6. And zoom standard isn't always the solution for us, but it once again appears like it goes on to the left forever, on to the right. Does that make sense when we look at the function? Sure, I can take 3 times big numbers, and I can take absolute value of any kind of number I want. So there are no problems for x. So the domain has no restrictions. What do you think? We're going to have restrictions on the domain over here on 16 when we're taking a square root? Probably. Okay. Range, it appears like as I scan bottom to top, it starts at 0. Well, that would make sense. In fact, I can tell right now by looking at this thing, if I put in 5/3, I get 0. The smallest thing that can come out of an absolute value is 0. So g of x, the values that can come out of the factory, are greater than or equal to 0, or 0 including to infinity. Again, we could do the minimum test on that. Okay, then 71, 72, let's take a look at 72. Write the area of an equilateral triangle as a function of the length s of its size. You know what that's telling me right there? And this is part that eludes people, and I think it's just we're so anxious to get going with the math that we miss the notation here. Write the area as a function, write a as a function of s. That means my final answer is going to be a of s equals. Okay, we've got this equilateral triangle, and some of you are fresh off geometry taking this, and you may know the formula for an equilateral triangle, but if side length is s, s, and s, and this thing's equilateral, we can use the plain old formula. What do we know about area? Area is 1/2 base times height, where there's our height. Well, the good news, that would be 1/2. The base is s. Now, what is the height in terms of s? If this is equilateral, and there's 180 degrees in a triangle, this is 60 degrees, this is a right angle, this is 30, this is s on 2, half of s, and you may remember, I hope I didn't just lose my, yeah, I think I'm okay. You may remember that in a 30, 60, 90, the sides are proportional in this relation, short side 1, long side 2, and the longer leg is square root of 3. To get from this side to this side, I have to multiply by square root of 3. So h equals square root of 3 times s on 2. And therefore, h may be replaced by s on 2 times square root of 3. So we get s squared on 4 times the square root of 3 when we put that together. So a of s, area based on s, is s squared on 4 times square root of 3. And you have a similar problem like on 71, just dealing with some circles. We'll see how that one goes.